So today we're very happy to have Hitoshi Murayama here from Berkeley. And he's going to tell us about some exact results in QCD-like and chiral gauge theories. So please take it away.
Okay, thank you for having me today. And I'm actually talking to you from Japan, still early in the morning, 6 a.m. Kind of waking up, but hopefully I can stay awake for the rest of my talk. And I'm giving you this talk, and I'm pretty excited about this, that I think we came up with a new way of studying dynamics of gauge theories in a non-perturbative fashion. And so that's a subset of my talk today. And Chicago is actually a great place for this because, you know, the legacy of Nambu, I'm going to actually mention that later on. So I'm going to start with a slightly lengthy introduction about this. So when we think about QCD, and just imagine this is the first time you learn about QCD, then what you get told is that, okay, the protons and neutrons we are made of quarks actually, and the quarks are in there, but you can't take them out, you can never see them, right? That's what you learn in grad school. So the first reaction is that, okay, this sounds like an internet scam. And I just still had an email in my inbox about this kind of internet scam that, you know, you have to transfer funds from some deceased parents and all that stuff. You know, that's how you feel because, you know, everything's made of quarks, you never see them. And then you start feeling a little bit better when you get told, well, you know, actually there's a reason for it called confinement. So quarks are meant to be confined. So they're eternally present. And that's why you can never see them. And that still sounds like an internet scam. And then you get told something in addition. Okay, so if you actually go ahead and compute what is called the beta function, you find the coupling constant grows towards the infrared. And if you go to high energies, there's an asymptotic freedom. So if you go to very high energies, quarks behave as if they are free particles. And you can do even experiments on this. And I see David in the audience, so he's actually doing that every day. Not right now because the beam is off, but you know that you see nearly freely behaving quarks. But if you go to long distances, the quarks are meant to be confined. So you start feeling a little bit better about this. But we know that even asymptotic freedom doesn't explain confinement. For example, there are many theories where the theory is asymptotically free, but does lead to a conformal fixed point in the infrared. So this is still only suggestive, doesn't really tell you that confinement is what's going on in QCD. And in addition to this, there was another big puzzle, which is what Yoichiro Nambu is famous for, namely protons and pions are made of the same stuff. But we know the proton is pretty heavy particle. And compared to that, pion seems to be almost massless. So how come that the things are made of the same stuff, but they have such different masses? So still putting everything together, everything looks kind of mysterious. Then came some theoretical developments that made us feel even better. So this is still a qualitative picture. So concerning confinement, my late colleague Stanley Mandelstam proposed this idea called dual Meissner effect. Namely, if you assume that there are magnetic monopoles in QCD, and further assume that they're condensed in the universe today, then this is the dual, the electromagnetic dual of the usual superconductor. And usual superconductor, we see the condensate of Cooper pairs of electrons. And when the electric charges condense, then you find magnetic field to be squeezed in vortex lines. That's the Abrikosov flux of type 2 superconductor. So if you take the electromagnetic dual of this, if you assume that the magnetic monopoles condense in a universe today, then the electric fields get squeezed into the vortex lines. And because the electric fields then are squeezed into this flux tubes, then the energy of the electric field is proportional to the length. So if we have quark and anti-quark pair that are tied through this flux tube of electric field, then energy or potential energy between the quark and anti-quark would grow with the distance linearly. And that's what we normally mean as confinement. But to be fair, this is still based on the assumption that QCD for some reason got magnetic monopoles and they condense in the universe today. And similarly, Yoichiro Nambu actually came up with this idea of chiral symmetry breaking. So now, of course, we know that QCD-Lagrangian has a large flavor symmetry called SUN cross SUN cross U1 baryon chiral symmetry. And so it was an incredible foresight that he didn't know QCD-Lagrangian, but could actually find out that this kind of large symmetry may exist in the world of strong interactions. Then assumed that this large chiral symmetry is broken to the vectorial SUNF cross U1 baryon. And if you assume that, then you can understand why pions are nearly massless, because they are basically Nambu-Goldstone bosons of this spontaneous broken symmetry. So then you start to feel better, because at least you see the mechanism why the quarks may get confined and why pions are light. But still, we are not totally happy about this, because they are not derived from the QCD-Lagrangian. So we are still lacking this straight line going from the QCD-Lagrangian as the fundamental theory of strong interaction to confinement or chiral symmetry breaking. And that's where we want to do even better than these groundbreaking ideas, which made us feel better, but still not derived from QCD. So we start to feel even better when there was a progress in understanding QCD. For example, the seminal works by Seiberg-Witten in late 90s. And so if you start with the theory which has much greater theoretical control with the large degrees of supersymmetry, like N equal to super Yang-Mills, then they could first show that this theory has what is called the Coulomb branch, where the SU2 gauge group is actually broken to U1. And there's also singularities on this Coulomb branch, where they could demonstrate that there are actually magnetic monopoles or dions, which have both magnetic and electric charges, which actually become massless on a particular point on this Coulomb branch where this adjoint scalar field has a particular value. So the first thing is that there are indeed magnetic monopoles in SU2 gauge theory. And if you further break this theory from N equal 2 supersymmetry to N equal 1 supersymmetry, so slightly closer to the real world, and that can be achieved by introducing a term proportional to this adjoint scalar field into the superpotential, because there is the massless monopole when this field U on the Coulomb branch has a particular value given by the strong scale lambda. If you put these two terms together, then you can show that this monopole field, which becomes massless at this singularity, actually acquires an expectation value. And that's I think the first demonstration of monopole condensation, really going all the way from the fundamental Lagrangian to the monopole condensation, as originally suggested by Stanley Mandelstam. And other people further broke this N equal 1 supersymmetry to no supersymmetries at all by introducing the mass of the gaugino in this theory. Then this monopole condensation actually is preserved even after perturbation. So then you sort of see that the super Yang-Mills theory is now broken to no supersymmetry. So this is just pure Yang-Mills theory of the SU2 group does lead to monopole condensation, at least when the supersymmetry breaking is infinitesimal. So this is what's a great achievement. And then monopole condensation may be understood now as a consequence of the fundamental Lagrangian. But when you talk about chiral symmetry breaking, we are not there yet, because if you actually take the similar idea of starting with this highly supersymmetric theory, this theory actually doesn't have a chiral symmetry, because this theory, by definition of having this large supersymmetry, requires the coupling of quark and anti-quark field to this adjoint scalar, and the symmetry is already SUN vectorial. There's no SU2 left cross SU2 right symmetry. They have to transform together to keep this Lagrangian invariant. So you can't even talk about chiral symmetry breaking because it's already broken in the Lagrangian. And in addition, if you think about going closer to the real world by breaking supersymmetry down to N equal 1, and that was again done by this seminal series of works by Natty Seiberg, the theory seems to have two unusual phases that don't seem to mesh well with what we expect in non-supersymmetric QCD. So it still doesn't like we have actually explained chiral symmetry breaking starting from QCD-Lagrangian yet. So how do we connect this beautiful mathematically well-controlled theory of the supersymmetry to the real world. And that's basically the rest of my talk today. So just as an enlightening review of what Cyberg told us about what happens in this supersymmetric QCD. So he actually could work out dynamics of these non-perturbative theories all the way from no quark flavors at all to a large number of quark flavors. And there are actually many different phases which we didn't kind of expect in non-supersymmetric QCD. So when number of flavors is from 1 to number of colors -1, he showed the theory has a runaway behavior. Actually, the theory has no ground state. And the quark fields are, of course, fermions, but because of supersymmetry, they're superpartner of the quark fields. And the quark fields start to run away to larger and larger values. And the potential doesn't have a minimum, so keeps going away to infinity. So that's the result of the dynamics of theory with a few number of flavors. If you go up in number of flavors, when it reaches number of colors, then the dynamics shows something called the quantum moduli space of vacua. So they're infinitely degenerate, physically inequivalent set of ground states. They're all ground states with zero energies. And in much of this space of ground states, the baryon number is actually spontaneously broken. Again, that's not something you would expect in QCD, but that's the non-perturbative result in this theory. If you further go up a notch in the number of flavors, then he demonstrated that QCD leads to confinement, but no chiral symmetry breaking. And this is possible in non-supersymmetric theories because when there's no chiral symmetry breaking, you still have this large flavor symmetry, SUNF left cross SUNF right cross UM baryon. And because symmetry is not broken, then in the confined theory, composite objects need to reproduce all the anomalies of this SUNF left cross SUNF right cross UM baryon. And that's possible because you have a large number of fermionic composites, thanks to supersymmetry. But once again, that's probably not what you expect in non-supersymmetric QCD because the composites are basically mesons and baryons. There's not a whole lot of freedom in coming up with the fermionic composites to give you all the anomalies that are present in the fundamental Lagrangian. That's the 't Hooft anomaly matching condition. So it doesn't look like we can get that many fermionic composites in non-supersymmetric QCD. If you go to a larger number of flavors, the theory is even more bizarre. This is called the free magnetic theory. So what happens here is that the QCD sort of confines, and all the quarks are now inside some bound states like mesons and the baryons. But it turns out that when the theory becomes very strong, the baryon composite now breaks up into fragments which have fractional U1 baryons numbers, and those fragments behave under the free magnetic gauge group, which doesn't resemble the original gauge group of QCD, and that is what is called the free magnetic phase. And I will review all of these stuff in a moment if you're not familiar with them. But anyway, so the Cyberg worked all these things out. It's very convincing. I think nobody doubts these consequences of supersymmetric QCD, but still doesn't seem to mesh well with what we expect in non-supersymmetric QCD. When the number of flavor is larger, then he also demonstrated that theory reaches an IR fixed point, and that is something you may expect in QCD as well. So this may be already somewhat closer to non-supersymmetric theories, but it's also a super conformal theories. So we need to understand that too. And if you go to yet larger number of flavors, then the theory becomes IR free. It's no longer asymptotically free. If you go to infrared, then you have sort of the perturbative theory of the quarks and gluons. So this part is in some sense understood, but everything below still doesn't seem to correspond to non-supersymmetric theory. Now, what do we know about non-supersymmetric QCD? Again, thinking about this various number of flavors. And if you are close to the limit of the IO3 theory, where the number of flavors is 11/2 NC, and above this, we have IR3 theory. Again, this will lead to a perturbative theory of quark and gluons. So this is something we may say we understand it. And if you're thinking about large number of colors and large number of flavors, if we're just a little below this limit, then you can show that theory has the fixed point, called the Banks-Zaks fixed point. So in this case, the one-root beta function nearly vanishes. Two-root beta function is order nc squared, and it's just not below this point. So you can have the one-root beta function and two-root piece cancel against each other with a relatively small gauge coupling constant. So you can trust perturbative analysis. And then there is the infinite fixed point. So the theory does seem to flow to the infinite fixed point, and that's something you believe in. If you're just only infinitesimally below this line. But if you go the order one below this point, then you lose control because the fixed point is beyond perturbation theory. So we are not sure if fixed point survives if you go further below this point. If you're at the bottom of this chain, then talking about 2 or 3 number of flavors. And we believe that's where the chiral breaks, as Nambu pointed out long time ago, largely because of the experimental data. We are still weak theoretically to demonstrate that this is indeed what happens. We can't derive this from fundamental Lagrangian, but we believe it because the data supports it. And these days, of course, lattice QCD simulation has gotten a lot better. So we see that you can extrapolate the finite number of quarks to nearly massless quarks from lattice QCD simulations, and see that there is the Q-cuba condensate. Pion does seem to become light, but you can never simulate massless QCD on the lattice because then pions wouldn't fit on the lattice. So we're getting better, but not quite to the limit where we want to be yet. And in between these two limits, we basically have no idea what's going on with non-supersymmetric QCD. So we tend to assume that the chiral symmetry breaking persists up to a larger number of flavors, but we don't know how far. We tend to assume that fixed point behavior persists that down to some order 1 below this limit of the IR freedom. And in between, there are some speculations. Maybe there is chiral symmetry breaking without confinement. People talked about all these different conjectures, but we don't have good theoretical control in between these two limits. So the basic conclusion of my talk today, and this is a takeaway, is the following. So if you perturb this n=1 supersymmetric QCD by infinitesimal SUSY breaking, but in a particular way called anomaly-mediated supersymmetry breaking, which is actually a very special way of doing so, and I'll tell you why in a moment, then all this complicated phase structure immediately collapses to 3 phases. From number of flavors 1 to 3½ NC, you can see that the chiral symmetry is broken. And from 3½ NC to 3 NC, you can also show that this leads to IR fixed point. And of course, above 3 NC, you still have the IR free theory. So all these complicated phase structure Natty Seiberg pointed out, which don't seem to connect well to non-supersymmetric QCD, immediately collapses down to 2 phases, which sort of start to resemble non-supersymmetric QCD. Then ideally, what you would like to do is start jacking up the amount of supersymmetry breaking to go beyond the strong scale lambda and see if they connect smoothly to non-supersymmetric limit. So if you assume that, then you have this phase structure of chiral symmetry breaking all the way from 1 flavor to 3½ NC, and IR fixed point all the way from 3½ NC to 3 NC. So this requires still some discussion because in principle, there could be a phase transition when the amount of SUSY breaking crosses the strong scale lambda, and eventually you want to send it to infinity. So from infinitesimal to infinity seems like a long distance to go, but I will tell you some argument why I might expect this is actually a continuous limit without encountering phase transition. Then at least you expect the universality class of broken chiral symmetry would persist to non-SUSY theory, or infinite fixed point would persist to non-supersymmetric QCD. So that is another argument I have to go through. But anyway, this is the main result I'd like to tell you today. So here's already the summary of the takeaway. So we start with a supersymmetric QCD worked out by Natty Seiberg. Most schemes to bring this n=1 supersymmetric theory to no supersymmetry do not have sufficient predictive power. But it turns out that special way of doing so, based on the idea called anomaly mediation supersymmetry breaking, is actually a good way of doing so, because this actually has a very special behavior called auto-white insensitivity. So the auto-white insensitivity means that even if you actually perturb this non-supersymmetric theory with a infinitesimal anomaly mediated supersymmetry breaking, you can make predictions even when you are facing the theory of composites like mesons and baryons, and demonstrate that theory collapses to expectations in non-supersymmetric QCD. So the combination of supersymmetry as a starting point and anomaly mediated supersymmetry breaking looks like it's a great tool to study a non-supersymmetric gauge theories in 4 dimensions. And this way we can now derive chiral symmetry from QCD. So that's the main takeaway from my talk today. So that's indeed the legacy of Nambu here in Chicago. And he was awarded Nobel Prize in Physics in 2008 for the discovery of the mechanism of spontaneous broken symmetry in subatomic physics. So if you believe this idea of chiral symmetry breaking, long-range, low-energy behavior of QCD is completely determined by the universality class of spontaneously broken SUN cross SUN mod SUN symmetry that will lead to massless pions as a number of Goldstone bosons. And that's the way we understand what QCD does. And hopefully I can convince you that the starting with supersymmetric theory with small perturbation of breaking supersymmetry actually does demonstrate this universality class of QCD. So that's the end of my lengthy introduction. And I have to also give you a little bit of introduction on what this anomaly mediated supersymmetry breaking is. And then we apply this to QCD. And once you see that it seems to work, then you also would like to understand this a little bit better when you have a rigorous definition of confinement in SONC QCD and demonstrate that there is indeed monopole condensation in non-supersymmetric QCD. And once you warmed up with this idea that this tool seems to work well, then you start to venture out into the uncharted territory. That if you go to chiral gauge theories, then we even don't have a good guess on what the dynamics of these theories are. And we can apply this technique in various versions of chiral gauge theories and work out the consequences, which turn out to be very different from what people conjectured in the past based on the idea called tumbling theories, and then conclude. Okay, so let me first get started with this idea of anomaly mediated supersymmetry breaking based on some of my earlier works. Oh, go ahead.
So your claim or the hope that there's no phase transition as you increase the mass, I guess would suggest that these special values of 3/2 NC and the other thing 1/2 NC, I forgot which one it was. That these are kind of still the same, I guess.
Yeah, that's right. That's at least my hope. Yeah, and so I try to come up with an argument for that. Yeah.
Is there evidence in lattice or some other methods that these values are special? That something happens?
So it's murky. So as you know, the lattice simulation with that dynamical fermions is a very difficult thing because the fermion determinant, Dirac determinant, is numerically very unstable. So if you increase the number of flavors, then the lattice calculus becomes more and more difficult, and reaches the equilibrium much more slowly. And there are limited attempts, of course, to do lattice simulation with a relatively large number of flavors with SU3 gauge theories, and the boundary seems to be maybe number of flavors is 6, 7, 8. 9. So that's the range where you start to see some transition, but these numbers are not firmly established. And if you go to even number of flavors, again, you see some hints that it seems to go to infinite fixed points, but when exactly that happens, or maybe there's some transitional phase in between is also still debated. So, so this range of number of flavors is still fairly poorly understood. That's where I think the fair summary of the situation. Does that answer your question?
Yes, yeah. And what about the conformal bootstrap? Are the Banks-Sachs fixed points visible there?
Well, the Banks-Sachs fixed point, of course, is known and established as long as you are only infinitesimally below this line.
Right.
And here, I can't actually apply my technique. This is beyond this IR3 limit in SUSY limit. So perturbing it, I can't actually reach this Banks fixed point from SUSY limit. So I have very little to say between these 2 points. From 3/2 NC to 3 NC, I'm going to make a bold claim that even though this is non-SUSY QCD, it leads to IR fixed point, and it may obtain emergent supersymmetry and become superconformal theory. And you may not believe that, and I didn't believe it at the beginning, but let me see how convincing argument I can come up with later.
Okay, thank you.
Okay. Any further questions at this moment? By the way, I really appreciate questions, so please chime in anytime you want. So what we like to do is to connect N=1 SUSY gauge theories worked out by Natis-Heiberg to non-SUSY gauge theories. So we need to basically decouple massless gauginos and squawks in these supersymmetric theories. So basically, we need to introduce supersymmetry breaking effects, mass of the gauginos and mass of the squawks to the SUSY gauge theories. But at the same time, as Natis-Heiberg told us, the theory turns into theory of composite objects like mesons and baryons. So even if you perturb the non-supersymmetric gauge theories in the fundamental Lagrangian level by introducing mass of the gauginos and squawks, you need to figure out what these things do on composite states like mesons and baryons. In particular, you have meson scalars, and you also have scalar baryons in supersymmetric gauge theories. And when you perturb the theory with non-zero gauginal mass and squawks, you need to understand how these massless mesons and scalar baryons acquire mass so that you can work out the symmetry breaking patterns in your universality classes. And what in particular is important is what their signs are. For example, when you have the scalar baryons, you need to know the signs of their mass squared. If it's positive, baryon number is unbroken. If it's negative, baryon number may be broken. And how do you actually work out the mass of the baryon composites from the fundamental gaugino and squawk masses is a challenge of non-perturbative calculation. So we need to have a tool for that. So just by naively introducing gaugino mass and squawk masses wouldn't do the job, because we really need to understand what they do on these non-perturbative composite objects of mesons and baryons. And there's actually a series of works done by Nick Evans and company and back in '95, soon after Heiberg came up with this series of famous results. And what they assumed is to just turn on the gaugino mass. And it's been known in perturbation theory that once you turn on the gaugino mass, that would also induce the squawk masses at the one loop level. So in some sense, one input would strike two birds at the same time. So maybe this is an efficient way of perturbing theory. And they also hope that this is under good theoretical control. So here I start talking about the superfield. So it turns out the gaugino mass is part of this multiplet of the gauge coupling constant in the gauge theory. And once you know how the theory works in terms of the strong scale, which is the function of the gauge coupling constant, because the gaugino mass comes together with the gauge coupling constant, maybe you can work out the consequences of the gaugino mass in a non-perturbative fashion, which actually does work to some extent. So if you, for example, work out the instanton effect from the non-perturbative physics, instanton effect is exponential of e to the minus 8 pi squared over g squared. And that comes with this theta angle theta, and also together with the gaugino mass. So this instanton effect is now coming together with this gaugino mass together with it. So they come together, and so they are under good theoretical control. So when you don't have any flavors of the massless quarks, then this is actually sufficient. So you can work out dynamics of non-supersymmetric QCD with no quark flavors by perturbating supersymmetric Yang-Mills theory with the gaugino mass. And that would lead to the condensate of gaugino bilinear. And the theta term also has non-trivial consequences. And you can talk about axion physics and all that. So this is very good. And so this is actually a very good piece of work. But when you actually do introduce the quarks, then you have to talk about something called the Kela potential in supersymmetric theory. And Kela potential is actually an arbitrary function of this instanton factor. In particular, its absolute value. You lose control on the theta angle and also control on the gaugino mass. In particular, when you ask the question, what happened to this meson composite, you would like to know the sign of the meson mass squared, but you can predict the sign in front of this term called the Kela potential. So you don't know the sign of the meson mass squared, so you don't know whether these mesons would condense or not condense. So what they had to do is to introduce a large enough quark mass so that you don't have to face this ambiguity of the result. So as long as SUSY breaking is smaller than the quark mass, then this sign ambiguity doesn't matter because the quark mass is large enough. Mesons would never condense. So if you want to take the non-SUSY limit by jacking up the size of supersymmetry breaking, you need to send the mass of the quarks even larger to avoid this ambiguity. Then you have to keep the quark mass very large and send it to infinity together with the size of SUSY breaking. And then you don't have the chiral symmetry to begin with, so you can't discuss chiral symmetry breaking. So this approach had a limited success, but the minute you want to apply this to chiral symmetry breaking, then it doesn't have enough predictive power. So we need to have a better idea on how to control theory non-perturbatively when you turn on the SUSY breaking effects, even when you're talking about the composite objects like mesons and baryons. So in particular, when you switch your description in the ultraviolet, in the theory of quarks and gluons, to the infrared, where you have the theory of the mesons and baryons, and you need to have a control on how supersymmetry breaking works when you switch description from UV to IR, and which can be done if you have enough of the external symmetries. So this is a well-known example that once you have a good external symmetry, then you can constrain how symmetry breaking effects enter the infrared Lagrangian. And the famous example is again, according to Nambu. So if you introduce quark mass in the theory of pions in chiral Lagrangian, you really switch the description from quarks and gluons in UV to the theory of pions in IR. But you can control how the quark mass effects appear in chiral Lagrangian. So in the UV theory, you have gluons and quarks, and you have the quark mass. And the quark mass seems to belong to this NF, NFS star representations of SUNF cos SUNF chiral symmetry. So if you write down the theory of pions in infrared, then you know how exactly this quark mass would enter the Lagrangian, because the only variable you use is this meson field. Now you switch description for UV to IR, and this meson field, it's a composite field, also transforms as NF, NF star under the symmetry. So you couple them together in this fashion. That's the only way you can couple the quark mass to this composite field according to the symmetry. And then you can make predictions on how pion mass arises as a function of the quark masses. And you predict pion mass squared goes like linearly with M up plus M down. So switching from UV to IR description, we have now theory of composites. But thanks to this large amount of symmetry, we can still control how symmetry breaking works in the lower description. Here's yet another example in QCD. Suppose you consider QCD in some non-trivial space-time background, maybe in the vicinity of the black hole or something. And we know exactly how the metric couples to QCD Lagrangian with the general coordinate invariance. And now QCD confines, you switch from UV description to IR description. Now you go chiral Lagrangian, but you don't have to worry about how this non-trivial space-time metric would couple to chiral Lagrangian. Again, thanks to general coordinate invariance, you just couple the space-time metric to the chiral fields, and you know exactly what the Lagrangian is. So again, thanks to a large symmetry you have in your theory, you have a control, even non-perturbatively, on how symmetry breaking works in the IR description. So we try to mimic this with the supersymmetry breaking too. And that can be done with the idea called sequestering. So suppose you break supersymmetry with some theory of fields, and we don't care what that actually is. And so the theory in the supersymmetry coupled to gravity is called the supergravity. And supergravity theory is known to have this kind of form of the potential. You have a positive term and negative term, and they have to balance against each other to get a zero cosmological constant, which is fine tuning. And that's the cosmological constant problem we are all aware of. But that's something you have to do to get the consistent space-time background. So you just assume that supersymmetry is broken in some way with non-zero f squared term, which is canceled by non-zero 3w squared term, and with a zero cosmological constant. And that would lead to non-trivial quote space-time background of supergravity. And the supergravity is now broken to regular gravity because spin 3/2 gravitino, would acquire mass. And that's the analog of the Higgs mechanism that the gauge boson eats a number Goldstone boson and becomes so massive. So in this case, gravitino eats Goldstino, spin 1/2 Goldstino from spontaneous supersymmetry breaking and acquires a mass as a consequence. So that's the super Higgs mechanism. And this is well understood. And once the gravitino acquires a mass, then the gravitino mass is a messenger to tell your gauge theory that supersymmetry had been broken somehow. And that will lead to supersymmetry breaking effects like the gaugino mass and squark masses in the gauge theory, which is Planck suppressed, coming from this negative term given by the superpotential W. And the word sequestering means that there is no direct interaction between whatever breaks supersymmetry and the gauge theory of interest. And if there's no direct interaction between them, the only effect of supersymmetry breaking comes through this super space-time background of the curved superspace with broken supersymmetry. So in similar to like black hole background in GR, you have a curved superspace because supersymmetry had been broken in superspace direction. And that quote space-time background would couple to the gauge theory. And even when switched to the infrared description of composite mesons and baryons, then original super GR invariants would tell you how exactly SUSY breaking effects appear in the IR description of the theory. So that's the idea. And that is achieved basically by the multiplet in the supergravity stuff, which is called the Y compensator. So we just need to know how this curved super space-time background would work. And that works through this field called E in my notation. And this E field is sort of like a Fierbein determinant, which has this the supersymmetry breaking effect M at the higher orders in super space theta. This is the fermionic coordinate theta. And we know exactly how this E with SUSY breaking effect would enter your Lagrangian with E star in a Kela potential and E cube in superpotential. So this is all dictated by super coordinate invariance. So there is no ambiguity there, even if you switch to the IR description of the composite meson and baryon fields in the Kela potential and superpotential. So all effect of SUSY breaking is now encoded in this single parameter M. And if you just look at this theory, then it looks like you can scale this E SUSY breaking effect away if you change the normalization of your field, chiral superfield phi, by 1/E. And if the Kela potential is the usual canonical one, phi star phi, and if your superpotential is dimensionless coupling, like phi cube, this corresponds to phi the fourth theory in non-supersymmetric theories, then you can absorb this power of E into phi by this rescaling, which turns out to also absorb all of this E cube into phi, then you completely lose supersymmetry breaking effects. So the morale of this is that this particular way of breaking supersymmetry doesn't lead to any supersymmetry breaking if your theory has only dimensionless coupling constant. Namely, if your theory is IR free, then supersymmetry breaking effect is 0. So it somehow has to do with the conformal invariance. But if you do have dimension 4 parameters, like a mass of the field, so in addition to dimensionless coupling lambda, now you have a mass for this field phi. And after the same scaling, you can absorb this E SUSY breaking effect into the field, and same thing gets absorbed into the field. But here I have one power off, from cubic power to second power, so 1 power remains. So the mass term now acquires supersymmetry breaking effect. So in general, when your superpotential has dimensional full parameter, then it's not purely cubic power in the field. And if you have square, then this power is 2. 2 minus 3 is -1, that's non-zero. Then you have supersymmetry breaking effects. So this is a 3-level effect of supersymmetry when you have dimension 4 parameters in the theory, which turns out to be generic in QCD-like theories because you have dimension 4 dynamical strong scale of QCD where theory becomes strong. So once you have strong dynamics, that will lead to SUSY breaking effects. So that's one important fact. But even when your theory looks like it's IR-free, namely that you have only dimensionless coupling constants, quite often dimensionless coupling constants also run because the regularization of theory requires a cutoff scale. Cutoff scale is dimension 4. For example, wave function renormalization is a function of the ratio of your renormalization scale over the cutoff scale capital M. And as I told you, any mass scale would acquire SUSY breaking effect. So this cutoff scale turns out to acquire SUSY breaking effect through this wild compensator E. And because this E can be expanded in power series in this theta squared, so I expand this the wave function renormalization factor into derivative with respect to mu over ME. And I have the first logarithm, which comes with anomalous dimension. I have the second logarithm, which corresponds to log derivative of the anomalous dimension and ... So you know how SUSY breaking effects enter this the Kela potential through anomalous dimension and the derivative out of the anomalous dimension. So you stick that into your Lagrangian with the kinetic term, then you can work out what the SUSY breaking effects is, again, without any ambiguity, and you make a prediction on how SUSY breaking effects enter through the anomalous dimension and its derivative. That turns out to give you the non-zero squawk masses proportional to the derivative of the anomalous dimension, and also non-zero SUSY breaking, what is called trilinear coupling through the anomalous dimensions, again, with no ambiguity. So all the SUSY breaking effects are determined only by these running effects, and running effects are known to be computed by physics at that energy scale of interest, depends only on the massless particle content at that energy scale. So it doesn't matter what you have integrated out of your theory in the UV, so your prediction on SUSY breaking effects is insensitive to the UV behavior of the theory. So in particular, even if you switch from the UV description of quarks and gluons to the IR description of the mesons and baryons, it doesn't matter. You know still exactly how SUSY breaking effects appear in your theory of mesons and baryons because the effect is UV insensitive. Now, this property seems too good to be true, but you can verify this very explicitly and also work out these consequences. Okay, go ahead.
Yeah, I had a couple questions.
Go ahead.
So the first is about this UV insensitivity. It seems to be a very strong claim to me. Is the claim that this sort of theory, since it's sort of insensitive of the UV physics, does that say that at high energies, the theory does again become supersymmetric, some sort of like misaligned supersymmetry?
No, in this UV theory, you can work out this the anomalous dimension of the fields in perturbation theory, and you predict the SUSY breaking effects are there, in particular squawk masses. So when your theories are asymptotically free, you predict positive squawk masses as a consequence. Even sign is predicted here. And you know the squawk mass is positive. So therefore, you can send this M to infinity in the end to go to the non-SUSY limit of the theory. So everything is predicted by the single parameter M once you know the dynamics of the theory.
My other question is, so we're doing this deformation by this background superfield, but in a way that does not preserve supersymmetry. So usually the sort of supersymmetric non-normalization theorems say, you just treat it as a background superfield and everything's supersymmetric. So there's no other terms that are generated. But in this case, since we're breaking supersymmetry, why should the background field, why should M sort of always come nicely with this curly E? Is that obvious? Or I mean,
Yeah, so that's because of really the supergravity invariance of the theory. So this chiral superfield E is supposed to be basically what's eaten by the gravitino multiplet to give mass to the gravitino. So it has to be chiral superfield that gets eaten by the gravitino. So that's why it has to always come with this combination, and no other combinations are allowed. And you might complain that we have this Kela potential, which depends both on E and E star because it's non-holomorphic. But it still is the case that it comes with the E star E combination. It's sort of the analog of the Vierbein determinant in GR. So the idea is still exactly the same as what we talked about with, for example, the chiral Lagrangian. Quark mass does violate chiral symmetry. But we know how this violation of chiral symmetry appears in the chiral Lagrangian a la Nambu and make predictions out of it. So the fact that chiral symmetry is already broken shouldn't deter you from writing down the chiral Lagrangian with chiral symmetry breaking effects, because you know exactly how that enters in the low energy description. In the same way that you have non-Minkowski background for QCD, but you just couple that non-Minkowski background to chiral Lagrangian AIR. So that's the same story. It's not Minkowski theory, but because we know QCD leads to IR description chiral Lagrangian, you just couple the same metric to the theory. And the back reaction of QC dynamics to the space-time metrics is suppressed by the Planck scale, so you can definitely ignore that. So that is the consistent treatment. So what I'm saying is that it's exactly the same story. So once you have the original supergravity theory, where you know how Y compensator appears in the Lagrangian, and because of the sequestering, only impact of SUSY breaking effect appears through supergravity multiplet with this Y compensator field, you can work out exactly how SUSY breaking effects appear in your description, and hence you can make predictions on what the SUSY breaking effects are. So that's the argument I'm making.
so you're
I hope that makes sense.
So you're saying the Weil compensator field is sort of like trying to make the theory conformally invariant, right?
Yeah, that's right.
Okay.
And that's the analog of the quark mass, non-zero quark mass in chiral Lagrangian. So you're right, you have broken supersymmetry, but you know how the effect, what SUSY breaking effect appears in your theory. Okay. I have some other voice.
I wonder if there is
question?
a sign ambiguity in the superpotential term.
No, there isn't, because you stick in this E star E in a way that this still needs to give you the positive kinetic term. So this one part gives you kinetic term, it has to be positive, you know the sign. And then this M part comes with theta squared M, theta bar squared M star. So it's M star M, so that's a positive definite combination. And then you can integrate over theta and theta bar, so you know the sign. So
Yes,
there's no ambiguity there.
Sorry, I meant the superpotential, whether it should come with the plus or minus sign.
Oh yeah, so the superpotential does depend on the sign of theta squared. So that it basically becomes your convention issues when you work out this trilinear coupling I mentioned earlier, and also the gaugino mass. The only relative sign is physical, not the absolute sign.
Okay, that answers. Thanks.
Okay. So I told you how the scalar masses can be worked out, and I'll tell you how the gaugino mass can be worked out. Again, the gauge coupling constant runs as a function of the renormalization scale of the cutoff scale. Cutoff scale acquires this mass at the SUSY breaking effect. Again, you expand. The first derivative is nothing but the beta function of the gauge coupling constant, which comes with the gaugino mass now. So this is the gaugino mass, which is given by the beta function of the theory. Again, in the UV, you can compute the beta function perturbatively and predict that there's non-zero gaugino mass. So when you send the SUSY breaking to infinity, gaugino mass does go to infinity. Again, this is determined only by the physics at the energy scale of interest, and is UV insensitive because it depends only on the beta function at the energy scale of your interest. So that's again the UV insensitivity. So as somebody asked, this seems like a strong claim, so you better do a test on this. So what happens? Anyway, just a summary of what I derived so far. When you have a tree level piece, with dimension 4 parameters in the theory, that's something you can work out immediately from the Lagrangian. So it picks up dimension 4 parameters in superpotential. And if you don't have dimension 4 parameters, you still have dimensionless coupling constants that may run. And as a consequence, you predict the gaugino mass from beta function of the gauge coupling and scalar masses from the enormous dimension factors. So, while compensator couples in a way that it makes your theory conformally invariant, so the SUSY breaking effects appear only from the violation of conformal invariance, which is the running coupling constant and an enormous dimension factor. So this all makes sense from the regard, but we like to also see if this UV insensitivity really makes sense. So if you look at the gaugino mass, for instance, and when you cross the threshold of some massive particle you integrate out, then beta function jumps from one value to another. So the gaugino mass also jumps if you believe this prediction. And it turns out that when you actually integrate out some massive particle, the mass of the particle receives a tree-level supersymmetry breaking effects, as I mentioned earlier. And if you stick that into this loop diagram, you induce the gaugino mass, correction to the gaugino mass, from tree-level SUSY breaking at the one loop level. So that's a one loop correction to the gaugino mass, which precisely corresponds to the jumping beta function, so that this formula is true both above and below the threshold of particle you integrate out, so that this formula is true at the energy scale both above and below this massive particle. So that's already a non-trivial test of this formula. If you like to test that this formula for the scalar mass is also true, then you have to go to two-loop calculations, but that's something you can do. I did with my students back in 21. And again, you predict that tree-level effect of SUSY breaking now appears in the two-loop diagram and gives you two-loop correction to the mass of the squarks. And so this formula jumps because enormous dimension factor jumps with the theory with the heavy particle and theory without the heavy particle. But that jump is precisely given by this induced correction at the two-loop level to scalar masses. And so this formula is again true above the scale and below the scale. So at all scales, again, that's the UV insensitivity. So when Steven Weinberg was writing his famous textbook on quantum field theory, somehow he was very puzzled by this behavior. And he sent me an email one day, how come this can be true? The right-hand side runs, but here's the mass. And I was very perplexed by this naive question. Of course, he should know that you can define gaugino mass in the way as a running mass, and both sides run. And you can even show that both sides run in the same way at all orders and perturbation theory. So this formula makes sense. And I responded this way, and he, went back. He apparently thought about this for about 1 week, and he wasn't annoyed by email. And he came back with yet another question in a week, which was now not naive at all. He was all the way down to the really depth of the subtle theoretical issues and asked questions about the regularization and all that stuff. And so, that's apparently he is. At the beginning, he sounds maybe a little bit dumb and asks very naive questions, but of course, he thinks through every problem completely on his own. In the end, he understands everything much better than everybody else. So I experienced that firsthand, and it was really amazing. So I was very honored when he thanked me in the preface of the volume 3 of the Weinberg's textbook, and he has an entire section devoted to anomaly-mediated SUSY breaking. So I'm running out of time, but at least I'd like to finish this QCD part of the theory. So I apply this idea of anomaly-mediated SUSY breaking in the QCD. So as I told you, Seiberg worked out the dynamics of the theory, originally together with Ian Affleck and Michael Dine. So you have a description in IR in terms of this meson field, and you have this inverse power superpotential that will lead to runaway behavior. But when the field value is large, then meson field has large value, where the field for the quark is very large, where theory is weakly coupled. So you can treat this meson field as if this is the perturbative quark field and work out the potential for it. And now, together with the SUSY breaking effects coming from this anomaly mediation, because the scale lambda is dimension 4, you get this tree-level effect. So both of them seem to be running away, but this M can have a phase, and your theory always chooses the phase of the field where this contribution is the most negative. Then it turns out that this runaway behavior in supersymmetry theory gets stabilized by the supersymmetry breaking effect with a lower power in field, which looks like this, and that develops a stable minimum, where this meson composite field acquires an expectation value. So for small SUSY breaking, the expected value is large, where the gauge theory is broken with large field values, and therefore you can trust the perturbative description of your Kela potential, and therefore this is theoretically consistent. Then you know the SUN cross SUN symmetry is now broken to SUNF vector symmetry. And so this would lead to, of course, chiral Lagrangian using the imaginary part of this meson field. So that's the proof of chiral symmetry breaking, basically proving Nambu's assertion long time ago. And you can also induce the Vesuvino term for the pi 0 to gamma gamma decay from the loops of the fermionic mesons, mesinos, now that they acquire mass from SUSY breaking. So it leads to the full chiral Lagrangian as the consequence of this supersymmetric gauge theory now perturbed with anomaly mediated supersymmetry breaking. So you conclude that this analysis will lead to spontaneous breaking of chiral symmetry, and you have Nabu-Goldstone bosons. And so that's the consequence. On the other hand, when you have only one flavor, then you have only one component meson. And so there's no massless direction orthogonal to this field direction. So this field direction is now massive. And so there's no Goldstone boson, the theory is gapped. And that's something you expect in QCD too, because of the U1 problem. If you have only one flavor, then eta prime meson has anomalous chiral symmetry. So it's not protected, so it becomes massive, and from the instanton effect, and therefore there's no Nabu-Goldstone boson, theory has a mass. So you actually derive these consequences in QCD from this very simple analysis of perturbing Seiberg's result with infinitesimal SUSY breaking effects using this special way of anomaly mediation. When number of flavors equals number of space, this is when Seiberg told us that you have this quantum modified moduli space where meson and baryon fields obey this relationship. And then their fermionic components satisfy non-trivial anomaly matching condition. So we know the meson and baryons are dynamical fields with a regular kinetic terms. And we can always go to canonical normalization for them. You don't really know the normalization of the Kela potential, so you can predict the size of the coupling constants, but you can estimate them in at least a large NC, or what is called the naive dimensional analysis. And then if you actually do this estimate, you know the typical size of these couplings, and they are dimensionless. But the scale lambda is dimension 4. So again, anomaly mediation would tell you how exactly that would enter your potential, and you can work out the minimum. You actually show that this X field acquires a VEV from SUSY breaking. Potential also is now non-zero and negative. And at this minimum, meson acquires this non-zero expectation value proportional to identity matrix. Again, SUN cross SUN is broken. So we now are proving Nambu's assertion for 3 colors and 3 flavors. And not only the pions are massless, now you can also show that baryon is massive. That answers the original question, how come baryons are massive, pions are massless? If you go to one further up number of flavors, this is when Seiberg told us that you have chiral symmetry breaking without confinement with the massless mesons and baryons. And again, we perturb this theory with the non-zero supersymmetry breaking with anomaly mediation, because you have this dynamical scale that will pick up the tree-level supersymmetry breaking effects. You can again work out the minimum. And the superpotential SUSY effect has this rising potential. So the potential actually looks like this in red. But together with the SUSY breaking effect, then you can choose the phase of phi with the minimum, so the most negative direction, which goes down with the lower power, which loses against SUSY potential at high power at large field value. So it develops a minimum somewhere in between. So at this minimum, again, you know the meson field acquires a VEV, and therefore the chiral symmetry is broken, that leads to massless pions. In this case, you can also show the mass of the baryon is basically 4 pi times the pion decay constant, and that's what you expect in non-SUSY QCD. And in this funny phase of the free magnetic theory, and you form this baryon meso composites, which now break up into pieces called the magnetic quarks. Magnetic quarks coupled to different gauge theory, which is IL-free, and also to this meson composites. And this coupling is dimensionless, so you get this loop level anomaly mediation, and you can work out the consequences, which look actually very strange. And I skip the technical details here because it seems to break SUN cross SUN chiral symmetry to SUNF minus NC, and baryon number is broken. And that's not something you would expect in QCD. And vacuum energy is also suppressed by the same loop factor. But it turns out that in this case, there's a deeper minimum without this loop suppression in a vacuum energy, where these meson fields acquire a large expectation value, not large compared to the original QCD scale, but large to the extent that you can integrate out these magnetic quarks. Once you integrate out these magnetic quarks with this meson field, then you can actually work out its low energy consequences, which is a super Yang-Mills theory because the quarks are now gone. Dynamical scale is now written in terms of the combination of the original dynamical scale and the mass of the dual quarks you have integrated out. So you again have this positive power in the meson field, together with SUSY breaking effects. Again, thanks to UV insensitivity, you know how SUSY breaking effect appears in your theory for the composite meson fields. You work at the minimum, and then you know the meson field condenses, again, chiral symmetry breaking. So that's the consequence with a large, now loop unsuppressed vacuum energy with a well-defined minimum with a chiral symmetry breaking. So what I have shown you so far is that this range of these weird phases by Seiberg all collapses down to the chiral symmetry breaking, which seems to match well with what you might expect in non-SUSY gauge theories. In this window of the IR fixed point, then you have IR fixed point. So the theory actually flows to infrared fixed point. You can predict the enormous dimension of the fields using the R charges due to superconformal invariance. You know exactly how these wave function normalization factors depend on scales. And once you do know that, then you can work out the SUSY breaking effects. And it turns out that you can work out the behavior of the gauge coupling constant, how quickly they approach the infrared fixed point values, which approaches by a power law, not logarithmic running like in massless QED. It approaches a fixed point value by the power law. That's very quick on the log scale. And when the coupling constant approaches the infrared fixed point by power law, then you can also work the beta function with this power law behavior. And beta function is what gives you the gaugino mass. So gaugino mass also gets suppressed quickly by the power law. So at the IR fixed point, then you have emergent supersymmetry. So even though supersymmetry is broken in UV theory, SUSY breaking effects disappeared in infrared. So you have emergent supersymmetry, and that's a superconformal field theory. And that's this IR fixed point here. So that's what I would expect the behavior in non-SUSY theory too. So the last bit, and sorry, I'm already going over time by 9 minutes, but let me close my talk by talking about why I might expect that there's no phase transition when you go across the boundary of the strong scale. And I have to say, I'm not super comfortable with discussion yet, but at least it looks plausible to me. So what happens when you jack up the SUSY breaking effects that go beyond this dynamical scale? So it turns out that both the size of SUSY breaking effect and dynamical scale are what Seiberg called holomorphic quantities. So this SUSY breaking effect originates from the superpotential in a sector that breaks supersymmetry, which is known to be holomorphic, namely it doesn't depend on the complex conjugates of any parameters in fields. Instanton factor of strong scale is also a combination of this multiplet of the gauge coupling constant in a holomorphic fashion. So that's also a holomorphic quantity. And if you compare holomorphic quantity to holomorphic quantity, you can take the absolute values. So you're not comparing M absolute value to lambda absolute value, but you really have to compare M and lambda on a complex plane. But what we know is the lambda is the nth root of this quantity. And so they correspond to nth root of some complex number. So they appear as isolated points on a complex plane. And when you jack up the SUSY breaking effects M from 0 to infinity, you can go smoothly without hitting lambda in between their phases continuously without having a phase boundary. And that's indeed the basis of all arguments Seiberg made on how to work out dynamics of SUSY gauge theories. You can go from 0 mass to infinite mass without phase boundaries. And therefore, all these theories are continuously connected to each other called deformation. And that's the holomorphy argument by Natty Seiberg. So that seems to work even when you have this holomorphic way of breaking supersymmetry, which is the way you do in anomaly mediated supersymmetry breaking anyway. So at least one can have an argument why you may not have phase transition when SUSY breaking effect becomes as large as the dynamical scale. But because dynamical scale is this unit circle, while the holomorphic value of the dynamical scale is isolated points on this unit circle, you can go from 0 to infinity without hitting any one of them, and therefore there's no phase transitions. So at least you can come up with that kind of argument. So I have to finish up now. So I complete the story with SU and C, and you can apply to SO and C, where definition of confinement is now rigorous because you have the on-screen Z2 center. And especially for the case of the NC-2 number of flavors, you have Coulomb branch where the monopoles become massless. And if you actually turn on the finite SUSY breaking effects, you can also show that monopoles acquire expectation value and hence condense at the singularity where meson field has a non-zero determinant. So you see the monopole condensation and chirosymmetry breaking happen together, and that's exactly what you would expect. And finally, we ventured out and applied this technique to chiral gauge theories, and that is actually a rather surprising result at the end of the day, but I ran out of time, so let me summarize. So combination of N=1 supersymmetry by Seiberg and anomaly mediated supersymmetry breaking does seem to be a great weapon to study non-SUSY gauge theories in a non-perturbative fashion. And when you apply this SUN QCD, you can derive chirosymmetry breaking with no ambiguity, or infrared fixed point, again with no ambiguity, for the small SUSY breaking. So this is the first time, as I'm aware of deriving chirosymmetry breaking from QCD Lagrangian for the first time. And if you apply to SON QCD, you can even show the monopole condensation so that confinement and chirosymmetry breaking happen together. And if you apply the technique to chiral gauge theories, I didn't have time to talk about, then people conjectured what these theories do, even though there's no good theoretical tool to work them out. And it turned out that our results seem to contradict with the past conjectures. And rather than having a large number of massless fermion composites people conjectured in the past, it seems to me that the gauge theories actually would like to minimize massless fermion composites by breaking as much symmetry as it can. So only to the extent it cannot have enough order parameters to break all the symmetries, it barely accommodates the massless fermions as a composite objects. Otherwise, you would like to break symmetry as much as you can to avoid them at all. So that seems to be the lesson I'm drawing so far. But anyway, so that's something I will tell you more if anybody's interested. Okay, that's it. And thank you for your attention.
So Hitoshi, I have a question. So then, what is the parametric dependence of the condensate on the supersymmetry breaking scale?
So it depends on which phase you are in. So if you are in this phase of the runaway potential, then the SUSY theory predicts that the field values go to infinity. And it is SUSY breaking that stops it. So parametric dependence is that the condensate of the meson scale with the strong scale lambda but enhanced by positive power of lambda over m. So in the zero SUSY limit, it does run away. That's the behavior Seiberg told us. But for finite SUSY breaking, it is stabilized at a finite value, but still much larger than lambda, where the field value is large and therefore theory is perturbative, and you can trust this potential. On the other hand, when you have larger number of flavors, the Seiberg told us that your theory is massless meson theory with this kind of steep potential. So in the SUSY limit, your potential has minimum at a zero meson value and hence confinement without chirosymmetry breaking. But with SUSY breaking, again, it develops non-zero mass, in this case suppressed by the ratio of the SUSY breaking over the dynamical scale. So this goes back to zero when you turn off SUSY breaking, but non-zero for the finite value. And when SUSY breaking scale is small, you deviate only just a notch away from the original origin. So again, you trust the description according to Seiberg. So that's the parametric dependence.
Yeah, I was wondering if you try to push the supersymmetric scale to large values.
Yeah, then you lose theoretical control.
Right.
You really do. But the question is whether universality class would persist. So what we learn in the QFD textbooks is that even when your parameters are changed and you might lose theoretical control, unless there's a phase transition, your symmetry structure doesn't change. And that's what we call the universality class, right? So even when you don't have the theoretical control anymore, if there's no phase transition, the fact that chirosymmetry is broken would persist. And that's the tool I'm using when you try to extrapolate from infinitesimal SUSY breaking to infinite SUSY breaking. So the real question in the end is whether you expect phase transition or not. And that's where I start to make an argument based on holomorphy.
I see. Very good. Thank you.
All right. Thank you for the question.
Yeah, I have one question on the holomorphy argument. So
okay, great.
Presumably it was made in a context where there wasn't dynamical supergravity originally.
Mm-hmm.
Are you not worried that in your case, you don't have an asymptotically free theory?
Well, you know, talking about quantum gravity, I have to say is beyond a pay grade of mere phenomenologists. So I can't really comment on the UV behavior of supergravity, but we are not deterred from coupling gravity to Kela-Lagrangian because the GR invariance dictates how the background metric couples the pions, right? So in the same spirit, I'm not deterred from coupling this curved superspace with non-zero SUSY breaking to the low energy theory of supersymmetric Yang-Mills or supersymmetric QCD, knowing how exactly these parameters enter the Lagrangian in the low energy description. So that's the philosophy I have here.
Hitoshi,
so it doesn't need to be UV complete theory. Okay, go ahead.
So Hitoshi, in the gravity case, you're preserving.
Okay, Seb.
You're preserving diffeomorphism invariance. So you can couple in the UV, you couple in the IR. It's all good. But here you're not preserving supersymmetry. So why is it reasonable to couple to say that this gives you more power?
Because of the same argument based on the Kela-Lagrangian. So in a Kela-Lagrangian, you are dealing with QCD, and QCD doesn't have chirosymmetry once you have the quark mass. But we first turn off the quark mass with the chirosymmetry, where you know that Kela-Lagrangian is the right description. Then you turn the quark mass back on, but we know how quark mass behaves under symmetry. And if that symmetry dictates how it can couple to the chiral field, then you know this is the conclusion. And then we make all these predictions by the properties of pions using Kela-Lagrangian. So it's the same spirit. Symmetry is already broken, but once you know how the symmetry breaking is controlled by this higher symmetry of the theory without symmetry breaking, the same symmetry controls your low energy description, then you can use that supergravity theory and know how the SUSY breaking effects enter the low energy description. So that's exactly the same argument.
But if you push your mass too large, then you never really had that control to start with.
Yeah, so I completely agree. I never said I do. So that's the only thing I can expect to persist is the universality class. And universality class means if you have chirosymmetry breaking with small SUSY breaking, and if there's no phase transition, when you jack up the SUSY breaking, then you have the same universality class with infinite SUSY breaking, and therefore you have shown the chiral-symmetry is broken. That's the argument. I never claimed that you have the control theoretically when you have a large SUSY breaking.
I see.
Does it make sense?
Mm-hmm.
Great.
Hitoshi, are there also an infinite number of corrections that are just suppressed by this, supersymmetry breaking parameter?
So you can try to do the expansion in, so the infinite number of corrections appears actually not because of the SUSY breaking. So as I said, the way this Y compensator appears in the theory is through this supergravity invariant Lagrangian. Therefore, the fact that this E star E enter the Kela potential and E cube enter the superpotential is dictated by supergravity. So there's no ambiguity here. The ambiguity exists when you don't have good control on the Kela potential, because the Kela potential may start out with a phi star phi. Once you know that 2th anomaly massing condition is satisfied that field, then you know the kinetic term is regular in phi. Therefore, Kela potential starts with phi star phi. But you could have also high order terms in phi star phi squared over lambda squared, phi star phi cube over lambda to the 4th, and so on. So you can have higher order corrections to it. And those higher order corrections now pick up dimension 4 parameter of the strong scale that would give you the tree-level SUSY breaking effects, and therefore that can lead to ambiguity. So that's where I can lose theoretical control, namely that when M is larger and becomes comparable to strong scale, field value phi also approaches the strong scale, both from above in a runaway behavior or from below with a composite field. Then high order terms in Kela potential becomes as important as the low order terms, and therefore that's how you lose theoretical control. Not because you don't have a control on biocompensator, but because you don't have a good control on the Kela potential.
Okay, I also have another question. So in doing this argument here on this slide, you did this sort of rescaling of phi by the biocompensator.
Okay.
On the previous slide, and then you show that all parameters, just all massive parameters, come with a biocompensator. It's like their effective scaling.
That's right.
When you do this field redefinition, is there any sort of weirdness that comes in from the Jacobian and the path integral?
Yes, that's exactly the superconformal anomaly. So because you do the rescaling, which is basically the superconformal transformation, and if the coupling constants run, then of course they pick up the non-zero Jacobian. And this is the way of working out the Jacobian in a way. So the one way you can actually come up with the well understood theoretical environment is suppose you have the SUSY QCD. And if you actually introduce additional super field in the chiral, the adjoint representation and additional flavors, you can lift it to n equal 2 supersymmetric theory with 2 NC flavors, which is finite, right? So then you have a finite theory. And from the finite theory, you can introduce mass for the adjoint chiral superfields and unwanted extra flavors you don't want to have. And those mass terms are part of the superpotential, and therefore their mass is a holomorphic. So now you have a fully regularized theory. In the absence of the mass term, it's finite. In the presence of the mass term, it is now regulated. And you know how SUSY breaking effect appears in the regulator mass. And therefore, you fully justify this treatment that all these renormalization effects would pick up SUSY breaking because of the regulator mass that comes with the SUSY breaking effects. So that's how I have the confidence to work out how the wave function normalization factor would lead to SUSY breaking parameters in the IR, precisely because of the non-invariance of the Jacobian due to anomaly of the conformal invariance, and hence anomaly-mediated supersymmetry breaking.
Okay.
Hi, I have one question about an S confinement part.
Okay.
So if you do have the number of color equals to 2, I can see that the second term in your tree-level superpotential vanishes. I'm just curious.
So sorry, which case are you talking about again? Can you tell me?
I'm talking about like NF equals to NC plus 1.
NF equals NC plus 1. Okay.
S confinement.
Okay.
If you choose the number of color equals 2, number of flavor equals to 3. So the second term in your tradable potential,
This one?
which is N minus 3, that's correct. Yes, that will be 0. I'm just curious to see, do you know the answer for this very specific case?
Yeah. So what you can work out is basically the same argument I have made earlier. So when NF is 3, and this treatable piece vanishes, because your non-perturbative superpotential is M cube, which comes with dimensionless coupling. But you still have the loop level SUSY breaking effects from this anomaly mediation, together with the SUSY effect. So with the loop level induced the SUSY breaking effects of the trilinear coupling, you can minimize the potential again and find the non-zero minimum with non-zero value for the meson and therefore chiral symmetry breaking. So analysis becomes a little bit more complicated because you have to work out your potential at the loop level. But I did that and verified that this is the consistent minimum.
Okay, thank you. Yeah.
You're welcome. So clearly I'm losing audience now.
Yeah, well, let's thank the speaker again.
All right, thank you for having me.